Okay, in this podcast I'm going to describe the history of the development of atomic models. You do need to know the scientists and what their major contributions were, what their key experiments were. So I'm just going to talk through this. You should pause and take notes along the way. Okay, it all started with Democritus way back more than 2,000 years ago. This is Democritus here, good-looking guy. He was a Greek philosopher, and he had a theory about the atom based on philosophy. So he's one of those guys that sat around at the beach and just thought about what kind of cool theories he could come up with. And he said, if you think about something like the sand on a beach, it looks like, from a distance, it looks like a one solid object. But as you get closer to it, you can divide it into smaller pieces. And when you get down to the smallest piece, that is going to be your atom. So he used the term atomos, which is where we got the word atom. And atomos in Greek means uncuttable. So when you get down to the last thing that's uncuttable, he said that was the atom. Okay, and then Aristotle came along about 100 years later and said, I don't believe what Democritus said. He said, rather, I think that all matter is made up of these four elements, fire, earth, water, and air. And he was also a philosopher. Neither of them had any data or experiments, but because Aristotle was a popular philosopher that most people admired, his theory, in fact, was believed for 2,000 years. Pretty incredible. People thought it was no such thing as atoms, but we had this Earth, kind of like this bad 70s group, Earth, Wind, and Fire. Okay. Then we went on to Dalton's atomic theory. Now, Dalton was the first one. This is 1600, so this is almost 2,000 years later. Dalton's theory was first one that was actually based on data. He did lots of experiments combining lots of different materials together to form compounds. And what he said was atoms are like smooth, hard balls that could not be broken into smaller pieces, kind of like the sphere idea, kind of like an 8-ball, this hard, round sphere. Dalton came up with 4 postulates based on his experimental work, and you need to know what those 4 are. So the first one says all matter is composed of small, indivisible particles called atoms. The second is that all atoms of an element are identical in mass and other properties. The third is that atoms chemically combine in small whole number ratios. So what his research showed was that you ended up with compounds that had, let's say, 1 atom of carbon and 2 atoms of oxygen, CO2, or 2 atoms of hydrogen and 1 atom of oxygen, water. And so based on that, he came up with this postulate, which was really pretty brilliant, that said atoms combine in small whole number ratios. And the last thing he said is atoms cannot be changed from one element into another, that an element is an element, it's unchangeable. Now, as it turns out, most of these postulates we still believe today. The only one that we don't quite believe entirely is this one, number 4, because there can be nuclear changes in elements that cause them to become a different element. But for the most part, he was bang on, just correct. Okay. In 1897, 100 or so years later, Thomson came along and did some work, and kind of by accident, he discovered the electron. So what he had was this tube. This is called a cathode ray tube, and it looks kind of complicated, but it's really, if you've ever seen one of those old-fashioned TVs before the digital ones, this is what used to be inside the TV box, okay? And regardless of what kind of gas he would put in here, if he attached a electrical supply or a magnet with the south and the north end, the high voltage negative and positive side, what he saw was that when the magnet or the electricity was turned on, that in fact the beam of particles did not go straight. That in fact there was a curve towards the positive or the negative. And what he saw was that the electron's path changed based on whether it was near the south or the north pole. And in fact, the beam was attracted to the positive pole, which told him there must be something in this stream of gases, regardless of which ones they are, that is negatively charged. And therefore, we came up with the electron as the discovery of Thomson. So he said, he actually said if an atom is neutral and there's these negative things, there must also be these positive things. And he did a lot of research trying to find the positive particles, and he couldn't. So he said it must be something like plum pudding. Now, plum pudding, this is called the plum pudding model. Plum pudding is really like a cake with little raisins inside, kind of like a chocolate chip cookie. He said this is a bunch of positive goo with these negatively charged particles embedded in it. So he is credited with discovering the electron. He suggested that atoms have negatively charged electrons embedded in a positive sphere. And because of his plum pudding analogy, it is called the plum pudding model. Now, Rutherford came along not too long after that, and he was actually a student of J.J. Thomson, and he was trying to develop more evidence for Thomson for his work. And he did this famous gold foil experiment. And what he did was he took these alpha particles, and he said if an atom is mostly positive goo with these little tiny electrons that are really have very, very low mass, that these beams, these positive particles, should go straight through. And what in fact he found was that almost all of the beams, when it hit this gold foil, now what he did was he took gold, he flattened it till it was really, really thin. He thought about an atom or a couple atoms thick, and he hung it up. And then he shot the beam through, and his theory was that the beam should go straight through and be detected on this detecting screen straight through. Okay? Here's this detecting screen. And what he found was, if he did 1,000 trials, that maybe 998 of them or 995 of them went straight through. But there were a few that were deflected, that actually didn't go straight, that either came off at small angles or, in rare cases, in large angles. So as you would imagine, as a scientist, he thought he must have done something wrong. So he did it over and over and over again. And he always got the statistically small number of trials where the beam came back. So he said there must be something here in the atom that the beam is hitting. So Rutherford is credited with discovering the nucleus. And what he said is because most of the beam goes directly through, most of the atom must be empty space. So this is what he saw. This is his view of what was happening, that most of the beams went right through because they didn't hit the nucleus. And then every once in a while there was a deflection. And the fact that it was a deflection said there must be something there that is small, positively charged, and dense. Now, his analogy was that it was kind of like shooting a cannon at a piece of tissue paper and having it bounce back. It was that surprising. So most of these went straight through, but every once in a while, if the alpha beam hit this small, tiny, dense center, it bounced back, which told him there must be something there. So he said the model looks something like this, that there is this small, all of the positive for the atom is concentrated in the center, and these electrons are around it. And the electrons, in fact, take up almost all of the space. This is tiny. Okay. So Rutherford's belief was the atom was mostly empty space with electrons moving around the center. Then we get to Niels Bohr. Several years later, and what Bohr said was that electrons move in specific orbits around an atom. So what he said is it's kind of like an onion. You have this positive center, and then you have these electrons that travel around in these concentric circles. And what he said was an electron can be here or here, kind of like a ladder. You can be on the first step or you can be on the second step, but you can't be in between. So that's what he said. You can be, electrons can be in what he calls this energy level or this energy level, but not anywhere in between. Okay, it's kind of like the stair step. So his model is often called the planetary model, because it's kind of like the solar system. Dense positive center with these electrons in these specific orbits that are circling around. Okay, so in fact we often draw the model when we talk about atoms. We often use Bohr's model, but it has been updated, and it is now believed that the more modern atomic model came out in 1932. And what it says is an atom consists of a nucleus that contains protons and neutrons surrounded by a cloud-like region of moving electrons. Something like this. So here's the nucleus, and then you've got this cloud of electrons. Now, we're going to talk a lot more about this when we get to the unit on electrons, but this is a probability model that the electrons travel in all different directions surrounding the electrons. Okay, so all you need to know is that the modern view is like a cloud with electrons moving in many different directions. Had a lot of similarities to Bohr's in that there's more likelihood that the electrons are going to travel in specific areas, but it's a little bit more specific than that, and we'll talk about that more later. So that's it.